and share my slide. Okay. All right, in this frequency response analysis, so here just to revisit what has been done. So before we go to the frequency response, normally in this case, we already have the topic about the open and closed loop analysis. So here just to share what has been done. In overall, we start with the what we call it open loop analysis, where in the open loop analysis we already covered the part of the balance. Wait a minute, I try to adjust the setting of my computer. Okay, sorry for the disturbance. All right. So in this case, we will try to revisit what has been done before. So in this case, what has been done is basically the open loop simulation. Open loop system. So when the open loop system is more on the derivation of mathematical model. So where the mathematical model consists of the three type of balance, which is known as the overall mass, component, and energy balance. So based on this mathematical model, we derive it one by one according to the state that has been required to represent the chemical process, where mostly the outcome from this derivation normally in the form of the first order or second order. So this is known as an open loop because here, based on the first order or second order transfer function, you may get the GP and GD, process transfer function and disturbance transfer function. So where the process transfer function here represent normally the variable that you want to control. While the disturbance transfer function, of course, since the name is disturbance, it represents what kind of input will interfere your total response. So since this one, both of these, you have the process, you have the disturbance, that means it is not possible to reach the required set point value. So thus you need the closed loop system. So where the closed loop system, normally we will have it the additional transfer function. Instead of GP and GD, you also have the GV, the GM, and of course the GC, where the GC in this case may represent the P, PI, or PID. So basically, once we introduce the controller inside our system, then that means we need to have the criteria to evaluate the effectiveness of the controller. So this can be done by using the offset. The offset calculation where we try to see how far your total response from your set point. Can we get the value equivalent with the value of the set point? So we investigate different type of controllers such as the P, PI, or PID. Of course, in theoretical, when you have the integral term inside your controller, that means it is able to eliminate the offset, meaning that when you have the zero offset, the value that you want to maintain is maintained at the required set point value. So in order to make sure the closed loop system is effective and reliable, then we can supplement it with the stability analysis to see, do you get the smooth response or do you get the oscillatory response? Or do you have a stable system or you don't have a unstable system? So this is the requirement for the closed loop system when we have the offset and stability. And of course, if we want to calculate the controller parameter, then you can include it as a tuning method. So where the tuning method such as the direct synthesis, the internal model control, or the ITAE, integral time weighted absolute error method, it can be used to calculate what is your KC, what is your proportional gain, integral time constant, derivative time constant value. Rather than using the trial and error, we put KC equal to 1, tau I equal to 1, tau D equal to 1. This method provide the starting point rather than you put any kind of the value. Because just to note, every chemical process is unique. There is no standard guideline to assume your value. Sometimes, maybe you are lucky, you put KC equal to 1, then you get the good response. Sometimes it is not the case. That's why the tuning method is very important to provide you the starting point of the controller parameters value. Normally, in the open loop and the closed loop system, we emphasize the use of the step input. I think this one has been covered before, where in the step input, you just change the value from one point to another point. So if we consider it, let's say in this case, you have the input. The MV here represent your input. And the PV here is your controller variable. Control variable. The variable that you want to maintain. So normally, when we try to have the input, we change the input is based on the step. Why it is a step? Because you just change from one value to another value where you have like a staircase, and then here based on the step input, you get the response. So from this, for example, you may get the first order plus time delay model. So you get GP K exponent negative theta S over tau S plus 1. So this is known as the process reaction curve where you have the input and the output. So according to the first order, when your process reach 63.2%, then you can get your time constant. And here it should also show you have the tau D and tau C. Tau C stand for the time constant and the tau D stand for the time delay or theta. So basically in this case, is it appropriate to have a step input in the chemical industry? Imagine that in the chemical industry, they are operating the plant 24 hours a day. So that means the plant is kept running in order to meet the continuous demand. They just stop it in case they have the plant shutdown or some of the occurrence in terms of the safety. Then they just stop it or they replace some of the equipment and so on. But if all of the equipment running smoothly, then they just operate it 24 hours a day, 7 days a week, 30 days a month. So this means it is not suitable to have a step input all the time, because here you can see this one is involved only one input value. Is it possible to have the change in the beginning and then maintain until the end of the operation? It's not possible. Sometimes they might change it. For example, you increase it, maybe you afterward you decrease it, you increase it, you decrease it. Depends on the situation. So when you have like this, that means another input needs to be used rather than step input. So this is the input, the different kind of the input. Sometimes we call it as a frequency. Where when you have the input increment and decrement like this, sometimes it can be represented as a sinusoidal input. So we take a look on the sinusoidal input. So in this case, you have the sinusoidal like this. So when you have a sinusoidal input based on the sinus, so this one is different compared to the step input. The step input you just increase or you decrease and then you let it maintain. Based on this frequency response, in order to adapt with the changing of the product demand or the process specification, we introduce the frequency. Based on the frequency, how frequent it is, your input needs to be changed. So to adapt that, we use the frequency response, where in the frequency response, normally we have the frequency W. So here the W is not for the frequency. Of course, when we have a frequency, that means we have the light oscillation rate, where you can see in this case, the graph show the increment and the decrement. So it complete one cycle. So where the P here is known as the period of oscillation. So where in this case, since we introduce the period of oscillation, that means you have another parameter that need to be considered. Where in this case, when we introduce the sinusoidal wave, we just set what is the frequency and what is the period of oscillation in order to ensure your input behave like sinus wave. So this is the thing that sometimes is important for the chemical process, where they need to keep the process running all the time. And if they make a changes, then it just based on the sinusoidal input, where you can reflect the changes by changing the parameter inside the sinus wave. For example, you just set the period of oscillation or the frequency based on your input. So the good thing about the sinusoidal, normally, if we take a look in this case, we can see that initially you have the slow rate of the sinusoidal. Based on the sinusoidal input, you can see initially when we have a slow rate of the oscillation, then it will give you the oscillatory response. But if we prolong the time, or if we increase the frequency of your sinusoidal, of course, your controller output will behave like this, up and down, up and down, up and down, where we call it this aggressive behavior of your controller output. However, the aggressiveness of your controller output contribute to the much better response. When you can see, after you increase the frequency, you can see you can have the good response over here, where it is very close to the 4 meter. So this example introduce the how to control the level using the sinusoidal input, where we want to maintain at 4 meters. So instead of using the step input, we use the sinusoidal input. In the beginning, the slower rate of oscillation is used. When the slower rate, you can see that the sinusoidal input at the slower oscillation rate produce the oscillation pattern like this. This is what we call it, oscillation pattern. So you can have the up and down oscillatory. But if we increase the frequency, we can see the controller output behave up and down, increase and decrease in the faster rate. However, when we increase the response at the faster rate, it contributes to the ability to maintain at the required value, which is 4 meter. Only here you cannot have the smooth response, but it is widely acceptable because in normal case, in the chemical industry, it is really impossible to reach to or to obtain the smooth response because the value is kept changing. For example, we cannot maintain the level at 4 meter all the time. Sometimes you need to have a deviation. Maybe the value 4.01, 3.95, 3.98, 4.05. It's like that. You cannot maintain at 4 meter all the time. It is impossible in the real process. Of course, in the simulation, you can do that. But in the real chemical industry, it is rather impossible to fix at one value. That's why, in this case, when we try to use the sinusoidal input, it can provide the good response. That's why here, another choice to evaluate our controller performance in the closed loop is by using frequency. So, in the previous chapter, we used the step input. A step input has been used to evaluate the performance. So in this case, rather than using the step input, we use another input which is known as a sinusoidal input. So this is the another strategy that can be adopted to measure the controller performance. Okay, this one is just the example based on the use of sinusoidal input and how the sinusoidal input, when we increase the frequency, it contribute to the much better response. So this means the main variable, the main important variable in this case will be your frequency. The higher the frequency that you may use, it can provide the good response. However, we don't know what is the frequency. So this is the topic of the subject where we learn how the frequency affecting your closed loop process. So consider a sinusoidal input has the following form where you have the xt equal to A sinus Wt, where the x is your input, the A is your amplitude. A stands for the amplitude. And the W here is your frequency. And the T here is your time. So in order to ensure you have the sinusoidal input, this is the following form. If you recall, when you have the step input, you will have, let's say, x over m over s based on the magnitude of the change. But in this case, it's a little bit different. So here, when we have the sinusoidal input, when we try to use to predict what is our output, then the following equation will be obtained, where you have the y prime t. The y prime here stands for your output. And then you still have the sinus. Of course, it is understandable when you introduce the sinus, you will get the sinus response in the end. Only here, when you increase the frequency, then you may not get the oscillatory response. And this oscillatory response will be damped and then force a straight line in the end. So based on this, the important thing for this is Ka divided by W square tau square plus 1, where this one represents the amplitude ratio for your case. The amplitude ratio means what is the peak, what is the height of your peak that can be obtained from your sinus symbol, sinus form of the input. So here, I don't go to elaborate to detail how we may get this one. This one is just for example, how the input and the output respond. The thing that I want to focus, if we have the first order response, normally we may get, there are two parts that we can obtain, which is known as the amplitude ratio and the angle. So this amplitude ratio and angle represent the magnitude of the change and the angle that you may get from the frequency response based on the different frequency. For the first order process, based on the sinusoidal input, the amplitude ratio that we can get is AR equal to K divided by square root tau square W square plus 1. Where this one originally it is from the G equal to K over tau S plus 1. So once you will obtain the transfer function, then we need to convert the transfer function originally in the Laplace. So in the Laplace, we want to convert into the frequency. So normally, based on this, the transfer function can be transformed into the form of frequency for you based on the amplitude ratio and the angle, where the standard form for the first order, K over tau S plus 1, is equivalent with the AR equal to K divided by square root tau square W square plus 1. And the angle can be obtained by angle equal to negative inverse tangent W tau. So how to get actually from the first order into this form? So this is the method where normally in order here, the idea is to change the Laplace into the frequency. Because the Laplace, you have the S. Now you want to use the frequency response. Frequency response is based on the W to represent the frequency. So how to convert it? So this is the step. Where the first step is to substitute S equal to JW inside the transfer function to obtain from GS to GJW. And then based on once you substitute the S equal to JW, we express the equation based on the R plus JI, where the R is only the coefficient, the variable for frequency, plus the J is the complex number, and I is the inverse. So based on this, we know that the output sine wave has the following amplitude. So this is the standard form for the output sine wave, where the amplitude, you have the A cap equal to A multiply with the R square plus I square square root. And the phase angle is based on the angle equal to inverse tangent I over R. So this is the standard equation, where to obtain the amplitude ratio, A cap over A is equivalent to the square root R square plus I square. So this is the step, the procedure, how to convert the Laplace transform into the frequency response. So we take a look the example. Now, in this case, we have the first order transfer function, Gs equal to K over tau S plus 1. So now our objective is to convert from GS, how we can get the AR equivalent to this, and how we get the angle according to this. Note that why we have amplitude ratio and the angle for the frequency response, because here the sinusoidal output have the peak. The peak. When you see you have the peak, the oscillatory, it has the increment. So how big is the increment? What is the magnitude of the increment? Is determined by the amplitude ratio. And then the angle represent the slope. Sometimes you have a sharp slope, and sometimes you have a decrement slope. So the angle to represent the slope is known as the phase angle in this case, where here we just want to demonstrate how we get the amplitude ratio and the phase angle from the first order transfer function. So the first case is we want to substitute S equal to JW inside our equation. So when you convert it, so this one go to the S, and this one go to the S. So we substitute S equal to JW. So this equation becomes GJW equal to K over tau JW plus 1. So based on this equation, we can see there is no S. So because we want to represent it as a frequency. So the next step is we want to eliminate the J. J here represent the complex number. So in order to eliminate the J, then we multiply with the negative tau JW plus 1, negative tau JW plus 1. So when we multiply this equation, K over tau JW plus 1, we multiply with the negative tau JW plus 1 over negative tau JW plus 1 for eliminating the J. So in this case, it contribute to the following equation, GJW equal to K multiply with the negative tau JW plus 1 on the numerator. For denominator, we can see that tau JW plus 1 multiply with the negative tau JW plus 1. So this equation can be further expanded. So when we try to expand it, we start with the denominator, it become negative J square tau square W square plus tau JW minus tau JW plus 1. So here, that is why we include negative tau JW, because in the end, we can eliminate this term and this term. Tau JW minus tau JW can be eliminated. And we also know that the complex number represent J square equal to negative 1. So this is the standard expression for complex number. Or in some cases, they use I square equal to negative 1. It's still the same thing, referring the same complex number. Only in this case, they use the symbol of J. So we know that J square equal to negative 1. So this contribute to this part. Negative 1, negative. So it become positive. Negative multiplied by negative 1, you get the positive. So for the bottom part, we can get tau square W square plus 1. So here we already eliminate the tau JW. So you have tau square W square plus 1. And then only here, the problem is the denominator, where you still have the negative tau JW plus 1. So for this part, we know that according to the equation, R, the GJW equal to R plus JI. So we try to rearrange the equation according to the R plus JI, where here we expand the equation, you get K over tau square W square plus 1. And then plus J negative K tau W over tau square W square plus 1. So that means this part represent your R. And this part represent your I. So we have the R and I element. So the next, based on this, we put the modulus on our equation, where here the modulus, that means the frequency should be the positive value. And then square root R square plus I square, then you can get the following equation. In this case, we no longer need the J, we just take the expression of the R and the I. So when you have the R and the I, then that means the equation become K over tau square W square plus 1 square plus the negative K tau W over tau square W square plus 1. square. So you have this part where this represent the R square, this represent the I square. So once you obtain that, then we can expand our equation. So this equation lastly become the k square plus k square tau square w square. Once we obtain the numerator based on the square, and then divided by tau square w square plus 1, and then you put the square, because in this case you have the similar denominator. So what happened next? We can factorize the k, where the k right now, k square, we factorize it, then you have in bracket 1 plus tau square w square. And the denominator, you have tau square w square plus 1 square. So this means we can eliminate the term, the numerator term, because you have a similar term on the top and the bottom of your fraction. So lastly, you can get square root k square over tau square w square plus 1, where in the end, k square root, you get the original k again, and then the square root tau square w square plus 1. So this is how you can get the transfer function gs into the amplitude ratio. So in this case, this is the history, how the derivation, the procedure, how to get the amplitude ratio. And then we go next, we complete the amplitude ratio for amplitude for the phase angle is the same thing. Now it is the expression is angle equal to angle of the G, and then the equation that we are going to use is inverse tangent I over R. So we already have our I and R. So in this case, this is our I and R. We just use it. We include in the equation for the inverse tangent. We include the I and the R. So you have the I and the R, where the I is equal to negative k tau w over tau square w square plus 1. And the R is the k over tau square w square plus 1. So here you can see we have the similar denominator, which means this part can be cancelled. So you can eliminate the denominator for both denominator in the I expression and the R expression. Similarly, for the k, you can also eliminate it. So that leaves you the tau w inside the term. So this contribute to the inverse tangent negative tau w, where the negative sign can be located outside the expression, contributing to the angle equal to negative inverse tangent tau w. So this is the derivation, how to get the angle and the amplitude ratio from the transfer function. For your case, you don't need to worry because in your textbook, you already have the transformation, the frequency response form. You just need to you just use directly from the table inside your textbook. This one, this example is just to show you how you get the expression for the amplitude ratio and the phase angle. So meaning that in this case, if we take a look, the first order, you have the G equal to K over tau S plus 1. So in this case, the standard form for first order is the following amplitude ratio and the following phase angle. And this not going to change. You just adopt. You just take directly the AR and the angle. You don't need to worry about how to derive it. That is the just the derivation before what I shown you is just to give you the idea how you get the following term. And if you have a second order, this is the following form. So we just use whatever it is. And next, in this case, because in this case, we have so many transfer function, depends on the complexity of your equation. So for the first order, you have like that. For the second order, you have like that. So that means you can simply adopt it. Let's say in the case you have a rather complex equation, for example, higher order, then this is the step. So you just compare whatever you have and try to convert it. So in this case, let's take a look on this part. When we have the AR and the angle for the overdamped second order. So this is the direct part. If you have the first order or second order, we can take directly how to form our part. Or if you're not sure, then of course, we can try to develop it one by one. For example, in this case, let's say you have this. Let me show you how to convert the amplitude ratio and the phase angle step by step. So normally in this case, let's say you have the transfer function gs equal to 2 over 3s plus 1 and s plus 1. Where normally what I want to assign, let's say here I put the numerator as a GA, just for the symbol. And for the denominator, you have two parts, 3s plus 1 and the s plus 1. So this one, for the numerator, I put G1 and this one G2, just for the sake of the symbol. So here, I can put inside the table where I have GA 2, G1, 3s plus 1, and G2, s plus 1. So for this part, I want to convert this transfer function into amplitude ratio. So for this amplitude ratio, if you have a number, like in this case, you have 2, then since the 2, you don't have any s, it's just a number. So that means the amplitude ratio should be 2. It's not going to change. Whatever the number you have, you convert into amplitude ratio, still you get the same expression. So for this case, since the transfer function GA is equal to 2, then your amplitude ratio also 2. For the 3s plus 1, since you have the s plus 1, that means in this case, the equation should be tau square w square plus 1. Square root tau square w square plus 1. Where the tau for this case will be 3. 3 square, you get 9. So that means in this case, it becomes 9w square plus 1. So normally, you have the tau s plus 1, then the standard form should be tau square w square plus 1. It's not going to change. You just simply use it. You just change whatever the value of your time constant. For this part, since the time constant is 3, then 3 square, you get 9. So you 9w square plus 1, and then you put the square root. Similarly, it goes for the G2. You have s plus 1. The tau is 1. So 1 power of 2, still you get 1. So meaning that you have w square plus 1. So this is just to show you the step by step how to convert the transfer function into the amplitude ratio. So we complete the AR, then we can go for the angle. For the angle, if you have the number, then that means the angle will be 0. When you have any kind of number, the angle will be 0. Why is 0? So if we take a look on the, let's say you have the sketch, y versus t. You have 2. So 2 represent the straight line. When you have a straight line, that means it's only is based on the horizontal line. There is no angle. The angle will be accounted as 0 if you put the number. So that's why if you have any number, the phase angle should be 0. And when you have the 3s plus 1, this contribute to the inverse tangent 3w. Where normally the tau s plus 1, your phase angle is inverse tangent tau w. This one is standard inverse tangent tau w, where the tau in this case is 3. Only amplitude ratio, you have the square. For angle, you just take the original time constant. And lastly, for the s plus 1, this contribute to the inverse tangent w. It's not going to change in terms of your tau. So we have the transfer function like this. And then the next step is try to compile it in the form of the amplitude ratio. For the AR, normally we put the modulus GA over G1 and G2. So for the amplitude ratio, normally it is a compilation. So we put the GA over G1 and G2. So that means it's still the same thing like what you have in the original transfer function. So what we need to do is just to replace it. So the GA for the amplitude ratio is 2. And then the bottom part, 9w squared plus 1, multiply with the w squared plus 1. So it's like this. So this is how you get the amplitude ratio, where the arrangement is similar like the original transfer function. For the next step is to obtain the phase angle. So for the phase angle, so let's say you have like this. I just copy it. So here we have the AR, and then for the angle, normally the angle in the numerator will minus the angle in the denominator. So here you have the angle GA. You need to minus the angle at the bottom. Angle at the bottom you have 2. G1 minus angle G2. So this is the standard way for obtaining the phase angle in the case of this transfer function. For the amplitude ratio, you just arrange. Only you put the modulus. But for this angle, the angle of transfer function in the numerator, subtract the angle in the denominator, top minus bottom. So for this part, the angle of GA is 0, minus angle of G1 is inverse tangent 3W, minus inverse tangent W. So this is your phase angle for the given problem, where you have the amplitude ratio and the phase angle. It's very easy. Normally, this part represent one question. One question in the final exam. Everybody can score it because it's straightforward. So here the keywords is to convert the transfer function inside to become your amplitude ratio and the phase angle. So this is the way that we can change it. So let's take a look on another example. Let's say we have like this. In this case, you have the 2s plus 1 on the numerator. How we can get the amplitude ratio and the phase angle for the higher order transfer function. So for this part, so we have G as 2 over 2s plus 1 and 3s plus 1, s plus 1. So the difference in this example, we have another transfer function in the numerator. So let me show you one more time how we can construct the amplitude ratio and the phase angle for this transfer function. So we conclude we have first term, second term, third term, and fourth term. So let's say the G2 here is your GA. 2s plus 1 here is your GB. So here for the numerator, I put alphabet A, B, C, D just to differentiate the transfer function. And for the bottom part, 3s plus 1, I put numbering G1 and G2 just to differentiate it. So here we have the transfer function GA, GB, G1, and G2. This is my transfer function. So based on this, I have the GS here. GA is equivalent to 2. This one 2s plus 1. And this one 3s plus 1. And lastly s plus 1. So I have 4 terms. 2 on the top and another 2 in the bottom. So now I want to convert it into AR and the angle. So again, here, I just repeat for your understanding. If you have a number, when you convert into amplitude ratio, it's still a number. Whatever the number you have, you convert into AR, amplitude ratio, still represent number because the number represent the ratio. But for the angle, it becomes 0 because this represent the flat line. So that means there is no angle over the number. So for the 2s plus 1, it is based on the square root tau square W square plus 1. So here the tau is 2. So you get 4. 4W square plus 1. And for the angle, it becomes the inverse tangent, 2W. Like that. The same goes with the 3s plus 1. 9W square plus 1. and it become, for the angle, inverse tangent 3W. You just follow the same standard form. And lastly, for the S plus 1, it become W square plus 1. And the angle will be inverse tangent W. So this 4 term has been converted into amplitude ratio and the phase angle. So the next step, of course, we want to do the combination. So based on this, this is your GA and this is your GS. So for this part, you need to have the AR, where the AR here is based on the arrangement of your transfer function. GA multiply with the GB divided by G1 multiply with the G2. You just put the modulus inside the transfer function, where now the GA is in the GB, GA is 2. Your GB is square root 4W square plus 1 divided by square root 9W square plus 1 multiply with the W square plus 1. So this is the combination of your amplitude ratio. So where originally you have higher order, 2 to S plus 1 over 3S plus 1, S plus 1. Now it become 2 square root 4W square plus 1 divided by 9W square plus 1 square root multiply with the square root of W square plus 1. So no longer you have the S. Now you have the W to represent the frequency. And lastly, the angle. So you have angle at the top, GA plus GB. So you combine all of the angle at the top minus all angle at the bottom. G1 minus the G2. Angle at the top minus angle at the bottom. So this contribute to the positive tangent 2W minus inverse tangent 3W minus inverse tangent W. So this is the total angle for the case of higher order transfer function. So when we take a look, it's actually a similar thing like this, where you can get the amplitude ratio and the angle. What I show here is the step-by-step procedure in order to ensure you reduce the possibility of making mistake. So you do it one by one just to have a clear understanding. Once you acquire the knowledge, you become a good transformers for the frequency response, then you can do it straight away, no problem. This one is just the step-by-step procedure. So this one, I already show you the kind of the tau s plus 1 and the number. And in some cases, you may have the dead time, the time delay. So whenever you have the time delay, then when let's say you have the GS equal to negative theta S. So this contribute to AR equal to 1. And the angle is slightly different. It's no longer to have the inverse tangent, but you have the negative W theta. So this is the difference where we just change the theta inside our equation. Let's say, for example, you have exponent negative 2s. So AR still equal to 1. And then the theta here, the angle become negative 2W. So it's like that. So the process 0 or process lag is like what I showed before. So it's just the same thing. And here, what we are going to do once we obtain the amplitude ratio and the angle. Of course, in this case, the amplitude ratio and the phase angle is used for what we call it Bode diagram. In the Bode diagram, we employ both amplitude ratio and the angle to tabulate how the response looks like. So the Bode diagram is look like this, where in the bottom part, you have two graphs on the top and the bottom. The top graph here represent the amplitude ratio, AR. And the bottom one is represent the phase angle in the degree. So for this part, the y-axis represent the amplitude ratio and the angle. But for the x-axis, the horizontal line, it represent the frequency, W. So this means you will get the graph AR versus the W and the angle versus the W. Where normally the W, the frequency will be given. For example, in this case, you have 0.01, 0.1, 1, 10, 100. This is your example of the frequency. So in this case, let's say we have this kind of the transfer function. Let's say you have this amplitude ratio and the phase angle. What you are going to do is to plot the Bode diagram. In order to plot the Bode diagram, we will put the frequency inside our equation. So in this case, let's say we have W, frequency. So for example, based on this graph, it starts from 0.01 to 100. 0.01, 0.1, 1, 10, 100. So the W here, we substitute inside the equation. So you calculate what is the AR when you put W 0.01. Then you repeat the step by calculating AR at different value of frequency. The same goes with the angle. You put the value of your angle of your frequency inside your expression. Then you do the calculation. So once you obtain this value, then we will do the plotting. We will do the plotting of our Bode diagram. It's like that. So in this case, we will get this kind of graph. So this kind of the graph represent the Bode diagram, where you have the amplitude ratio and the phase angle. What we are going to do, okay, that will be discussed later on. So here I just illustrate what we can obtain from the amplitude ratio and the phase angle. So the next, just to share with you, of course, we want to observe the characteristic of our controller. So for example, when we try to use the proportional, the PI controller, what happened? So let's say here, first of all, we need to do the conversion. How we can convert the expression for controller into the frequency response. For example, in the case of the proportional controller, you have GC equal to KC. So when you have GC equal to KC, automatically you have the amplitude ratio equal to KC because the KC is a value. It's a value. And the angle will be 0 since any value represent 0 angle. They say you have the PI controller like this, where the form is GCS equal to KC 1 plus 1 tau IS. So this is the form of the normal PI controller. And lastly, if you want to convert it, this is the following form. You just take directly the form. And lastly, for the angle is the inverse tangent, negative 1 over tau W. So meaning that every expression, normally we have the form. You just need to take the form, the correct form for your respective controller. This is another example for the, if you have proportional derivative controller, GC equal to KC 1 plus tau ds. And the following is the AR and the angle. And this is for the PID. So this one, you can refer to the table 13.2 to 13.3 or in the page of 256, 258. Just to make it clear, normally you don't have the this kind of table in the recent textbook. In the 4th edition, you don't have this table. You only have it in the 3rd edition or lower edition. 2nd edition, 3rd edition, you have it. The latest edition, if I'm not mistaken, you don't have this kind of table. So better for you to have a soft copy of it in order to make sure you don't miss anything for the final exam. So this is the thing about the frequency response. So in this case, let's have one example in for the rest of our class. Let's say in this case, I give you one example. All right. Let's say so how to apply this kind of equation. All right. So based on this example, you have been given the transfer function of GP equal to 2 over 5s plus 1. The GD 1.5 3s plus 1. The GV equal to 1 over 2s plus 1. GM equal to 3 and GC equal to 2. So for this part, normally we want to observe the behavior of our closed loop performance. So when you have the closed loop, in this case, it represents the GP, the GV, the GC, and the GM. So this is the most common transfer function involved in the closed loop, in the loop. So here you don't need the GD because the GD normally is outside the loop. If you recall, you have the KM and then you have the GC, you have the GV, you have the GP. And then here you have the plus, you have the GD coming into the system. And then you have the GM back to the system. So here you can see that the GM, the KM and the GD is outside the loop. What we are interested is the loop itself. When you have the closed loop, it represents this loop only. So this is what we call it loop. So meaning that for this part, we just use the combination of the GP, GV, GC, and GM. So when you have the GP, GV, the GC, and GM, for this case, you just multiply all of the transfer function. So for example, here you have 2 pi s plus 1 multiply with the 1 over 2s plus 1. And then you multiply with the 3 multiplied by 2. So you don't need the GD. So based on this, 2 multiplied by 3 is 6, 6, 12. So total you get GP, GV, GC, GM equal to 12 over 5s plus 1 to s plus 1, like that. We just use PVCM because it is in the loop. Sometimes the GD is given to test your understanding. If you understand, then you know that the equation will not be used for the evaluating the closed loop. So for this part, you have 12 over 5s plus 1 and 2s plus 1. So I put the G equal to GP, GV, GC, GM equal to 12 over 5s plus 1 and 2s plus 1. So we have like this. So based on this, we can characterize it. So let's say this one, the first term, second term, and the third term. So here your GA, this one is your G1, and this one is your G2. So based on this, you have G12, 5s plus 1, and then 2s plus 1. So you have the AR, this one becomes square root, inverse tangent, square root, tau squared, 25w squared, plus 1. And then this one become 4w squared plus 1. So, and then here we put another one, the angle. So the angle for this part is 0. This one inverse tangent phi W. And lastly, inverse tangent 2W. So for this part, we can complete the AR. Where the AR is GA divided by G1 multiplied with the G2. So this contribute to the 12 square root 25 W square plus 1 multiplied with the 4 W square plus 1. And then the angle GA minus G1 minus G2 equal to 0 minus inverse tangent phi W. Inverse tangent 2W. So this is your AR and the angle for the given problem. So for this part, the next part is involve the Bode diagram calculation. So this is the equation. Where now, based on this, is your W AR and the angle. So we have the 0 0.01, 0 0.1, 1, 10, 100. So we have these 5 different W. So based on this, I think I just let you to calculate it. What is your W? What is your AR for this different W? So this is your homework for today class. Where right now, try to calculate the AR at different value of W, 0 0.01, 0 0.1, 1, 10, and 100. And then one more thing, I will give you the Bode diagram. All right, here is the Bode diagram. So this one I will share it with you. And this one also will be used in the final examination. So I will share in our WhatsApp group. So once you calculate all of the AR value here, you determine the AR. The next step, you need to include in the plotting. So you need to do the plotting for the amplitude ratio and the phase angle based on the given value from 0 0.01 to 100. So this is your task for today class, and will be discussed how to interpret the diagram, the Bode diagram, next Monday. So this is the task. feel free to contact me for the discussion if you require. So I think that's all for today. Thank you very much. Class is dismissed.
Thank you, Doctor.
Thank you, Doctor.